Hello everyone, this is Mr. Salceda with another video for Algebra 2 class. If you're watching this, it's been a while since I uploaded a video, but hopefully everyone here is doing really well. Okay, so I want to talk to you guys about the rational root theorem. Right? Previously, when we started working with polynomials, I gave an introduction on this definition, right? And everywhere you go, they sometimes use a plus b plus c and so on. In this particular case, they use a, where the sub value of the a and the exponent of n, it just gets subtracted as you go on until you eventually you get to the squared value, to the regular x, and finding your x sub 0, which is your constant, right? Now, for today's lesson, it's intimidating because some of the problems are very, very long, but they're just that. They're just long. Because at the end of the day, all we care about is working with the first value that has the highest exponent, which is the coefficient in this case, and the constant, right? The one that doesn't have a variable. So the one with the highest exponent and the one without the variable, usually those are the ones that we want to go for. And for the case of the constant, we call them p. Now, after we make this declaration, so once we find the coefficient of the term with the highest exponent, we call that the q value. And once we find out what the constant is, we call that the p value. So they're two different things. Now, every time you talk about p and q, we are talking about the positive and negative factors of those values. So they have to be plus and minus p, plus and minus q. And once you determine that, we can start using the rational root theorem. The rational root theorem sounds how it is. It's reasonable, right? It's within reasonable range of reach. Now, remember that roots are, we call them roots a lot, but they can also call them x-intercepts, they can call them zeros, or they can call them solutions. Let me fix that. You can call them x-intercepts, zeros, and solutions. Okay, so in this case, once you determine what p and q are, we're going to grab the factors of those guys, and all the values for the factors of p are going to be divided by all the factors of q. So here's the first example from your practice handout, and this one's pretty simple. Your constant, remember, that's always going to be your p. And on the other hand, your q value, again, you look for the one with the highest exponent, so the exponent is the highest. So therefore the 3 is a q. So what you do here is we're going to find the factors of p, so positive and negative p. In this case we have a negative 1, but we'll make it plus and minus 1. The factors of 1 is just the multiples of 1 times 1. And then for the factors of q, it's going to be plus and negative 3. And in this case, 3 is a prime number, so the only multiples for that one is positive and negative 1 and positive negative 3. Okay. Now, this positive and negative thing, it's only done for this particular section. You won't have to do it after this section. Anyway, so now what happens is we're going to use the rational root theorem. So the rational root theorem, which is this formula, remember that all the factors, positive and negative factors of p, get divided by all the positive and negative factors of q. So in this case, we will start listing them. So in this case, we only have one p, because since they're both 1 to 1s, we're going to repeat. And all these p's are going to be divided by the q. So the first one's going to be positive negative 1 over 1 and 1 over 3. And then if you can simplify, go ahead and simplify. So positive negative 1 and positive negative 3, a third. So what does this tell us? This tells us in conclusion, which I'm going to ask you guys to write this statement. So these three dots means in conclusion, therefore, hence, thus, entonces, in summa, in summary. So I know we only count two, but remember, you have a positive one and a negative one. Positive 1/3 and negative 1/3. So I'm going to write a statement where it says there are, or there exists, 4 possible solutions. In this case, rational solutions. So, I mean, if you don't mind saying that, so we have 4 possible solutions. However, this was a method that we used to do back in the day. So now, how do you prove which ones are your actual solutions? So, if you grab f of x, so f of x. So if you grab f of x, just to recap, you don't have to do it like the way I'm about to show you. So you grab f of x. Okay, and let's say you want to test one of these. So let's say you want to test the positive one. So if you test the positive one, okay, and let's say you get 1 times 1, well, that's 1. So 3 times 1, and 2 times 1, that's 2, minus 1. And then 3 times 1, that's 3, plus 2, minus 1. So that's 5 minus 1, so that's going to be 4. Now, in order for it to be a root, a solution, or whatever you want to call it, it has to be equal to 0. So in this case, positive 1 does not work out. Now let's try another one. So let's say we try negative 1. If we try negative 1, that really changes the dynamics. So 2 times negative 1, that's negative 2. And 3 minus 2, well, that's 1. And then minus 1, we get a 0. So therefore, the negative 1 checks out here. So it does happen where sometimes you do get the 0, right? So it checks up for that one. So now let's try to find another one. So let me change the color here. So now let's say we try positive 1/3. Now this one, I'm not the best guy when it comes to fractions, but let me just show you real quick, as fast as I could. So we're gonna try out the 1/3. So 1/3 times 1/3, that's gonna give you 1/6, only 1/9. And then 2 times 1, that's gonna be 2/3. So therefore, this is gonna give you 3/9 plus 2/3 minus 1. So therefore, this is going to give you, well, 3/9, that simplifies to 1/3 plus 2/3 minus 1. So 1/3 plus 2/3, well, let's check a third plus a 2/3, that's a 1. That's 1, and that equals 0. So the positive 1/3 works. And now if you try the negative 1/3, well, you're not going to get a 0. So my conclusion for this, so this is the way we used to do it. This is the way we used to do it back in the day when we didn't have graphing calculators. Of course, now we have graphing calculators, and we don't have to worry about using that. So now for the next problem, I'll just use decimals instead of using this method. But just know that this was the most practical way back in the day to find the solutions when you couldn't graph it. So there are 4 possible solutions for f of x. However, but only the negative 1 and the positive 1/3 are actual rational solutions. So just call them solutions. Or again, if you don't want to use the word solutions, you can use the word roots. You can use the word 0. In this case, it's an x. You're using the letter x. We call them x-intercepts, right? Now they don't usually call them x-intercepts once you go beyond this class. Just so you know. All right. So if you go to Google Classroom, I'm going by the practice handout you have. So now I'm going to do, let's try number 3. So now we're going to go ahead and try number 3. Okay, so number 3, again, what we're going to do for this one is that we're going to find our p. We know our constant. This is our p. And our q is going to be, well, again, the highest degree is 2, but I do not see a number. Now, just because you don't see the number, it doesn't mean it's not there. But since we read this as 1x squared, we already know that the number in front of it should be 1. So this is going to be my q. So now, as we use the rational root theorem, again, we get the factors of these two. So for the p value, we're going to get the factors of 10. So we're going to get positive negative 1, and 10 divided by 1, that's 10. And then we go ahead and try the 2. 10 divided by 2, that's a 5. And then, of course, if you do 3, it doesn't work out. If you do 4, it doesn't work out. And then you try 5, it works out. And you may want to write this. But remember that AB is equal to BA. I don't know if you guys remember this formula. So we don't have to do this one because we already have it as 2 or 5. So we don't have to rewrite it. So that's why we don't go beyond certain values. So now for Q, so positive negative Q, now this one is a 1, and the only multiples for 1 is just 1. Now, thankfully, it looks like a lot of numbers, but if the numbers repeat, you don't have to do them for 1. So in this case, for P, there's only 1, but then if you look at the Q, it has 2 2s. Well, technically, that's the same number, so we already have to use the 1. So technically twice, because the plus and minus, that tells us there's a plus and 1 and negative. But we see that's just 1. So now, we're going to use the rational root theorem. So P over Q. And it's going to give me, well, all the P's have to be divided by Q, but since there's only technically 1 by our view, we just have to write it as positive negative 1, 1, positive negative 2, 1, positive negative 5, 1, and positive negative 10. And when we simplify this work, we get positive negative 1, positive negative 2, positive negative 5, and positive negative 10. Okay. Now, as I said before, these plus and minus, the positive and negative, they're not there just to look pretty. You got to remember that the positive and negative tells us that you have a positive 1, a negative 1, positive 2, a negative 2, positive 5, negative 5, positive 10, negative 10. So therefore, we see 4, but since technically you have 2 of the same value, positive negative, you multiply by 2. So in this case, we have 8. So my conclusion is, right, you can say they are or there exists eight possible roots for f of x. But, and then now for this time, I don't want to use substitution. You know, we plug them in and we get outputs. I rather just use the graphing calculator to prove which ones are the actual ones. So if you open up Desmos, and hopefully everybody has become better acquainted with it, it's a free calculator, right? That you can take it to any math course. And we're gonna grab x squared, so f of x is equal to x squared plus 8x plus 10. Okay, and if you look very closely, what are my solutions? If I type it correctly, x squared plus 7x. Okay, so this seems to be off here. Let's see. X squared, what's up here? X squared plus 8x plus 10. So this seems to be off. So for this one, I guess I did something wrong. We check it out. None of these actually are actual solutions. So if you look very closely, we're supposed to either get positive 1, negative 1, positive 2, negative 2, positive 5, negative 5, positive 10, negative 10. So if you look very closely here, once we graph it, these didn't give us either of those values. Right? So the rational root theorem in this case did not really help us. So now later on we're gonna find out how to obtain these. Um, so what's gonna happen is that these are actually called irrational numbers. So the rational root theorem are not able to obtain the irrational values. So in this case, it did not work. So, but I would say none of these are actual solutions or roots. Let me use the word roots. Since f of x has irrational roots. Okay, so it doesn't always work. Okay, so let's move on to the next one. So we move on to the next one. So let's say like number 5, which is a much more better one. And again, it may look very intimidating, but they're not. So again, my P is my constant, and my Q is the coefficient of the term with the highest exponent. So in this case, the x25 is the highest one. So 4. So now when we gather the factors of P, so we're going to get positive negative 1 times positive negative 25, positive negative, well, we can't divide it by 2, we can't divide it by 3, we can't divide it by 4. So let's go ahead and divide it by 5. And that's the only one. So this only has 4, or technically 8 because we're positive negative. However, because of 5 repeating, this only leaves us with 6. Okay, so we don't have to use this extra 5. And now for the Q, we have positive negative 4. So we know the first one, but the next one, and again, we have the same situation we have with 5. 2's repeat, so therefore we only have to see it once. So therefore there's 6 for P's and 6 for Q. So now we're going to use the rational root theorem. And this is going to give me plus and minus 1. So for every P, you must divide for every Q. So 1 over 1, positive negative 1 over 2, positive negative 1 over 4, positive negative 5 over 1, positive negative 5 over 2, positive negative 5 4. Right? So it's up to you if you want to use this format or this format. Either one's fine. And then positive negative 25 over 1, positive negative 25 over 2, and positive negative 25 over 4. Okay, so the next step is to simplify. So if you simplify this, positive negative 1, positive negative half, positive negative 1/4, positive negative 5, and positive negative 5 halves, positive negative 5/4, positive negative 25, positive negative 25 over 2, and 25. Oops, don't forget the plus name. Okay, so in conclusion, if you count these, You have 1, 2, 3, 4, 5, 6, 7, 8, and 9 multiplied by 2. In conclusion, or therefore, there are 18 possible solutions for f of x. However, but whichever one you want to use. But and this one, if you graph it, you should get at least 2, I think. So if you graph it, this one, oops, to the fifth plus 2x to the fourth plus 30x to the third minus 15x squared plus 50x's minus 25. So this was a little weird if you look at it. So you may want to adjust the window for this one. So click the bar, and you may want to minimize it from -5 to +5. And then for the window, you may want to expand it to maybe -50 to +50. It's up to you. So in this case, the 0.5, if you type it in, f of 0.5, you get a 0. So in this case, we only have one of these. So the positive 0.5 was the only one that checked out. So, but only the half is an actual, or it's the real solution. So for this case, it does help us out, right? And now imagine having to substitute all these into the function like the one we did up here, right? So that's the part that makes it very scary for people back in the day. So imagine you get a list that was bigger than this. So so problems that have actually more terms and bigger coefficients, those are the ones that tend to have the most problems and the most complicated procedures. So this is how the rational root theorem was used back in the day. And since they have a graphing calculator, they will have to use all these until they get the 0. So now, for example, if I try to do 25 over 4, so if I try to type 25 divided by 4, I don't get the 0, so that's why it's not a solution. Or what if I do the 1? Again, I don't get the 0. Or what about the -1 over 2? I still don't get a 0. But if you just put the positive half, you get the 0. And that 0 is the reason why this is called a 0, right? Because when you input into the function, you get an output of a 0. So the name fits. And let me go ahead and just, well, actually, I think I already gave you guys a copy of these notes, but I'll give you the new ones. Go ahead, touch this one. Okay, so you don't have to use this method. You do not have to use the substitution method to verify to say which is your true answer. Now, if you can do this, you have a lot of patience. Right? I have my master's in that, and I gotta tell you, I don't have patience for this. And then just be very careful with these problems, because sometimes it makes you feel like you did it wrong, but you did it correctly. But the problem is that some of these problems, it doesn't work with the rational root theorem. I'll go ahead and revisit this problem later when we start getting irrational roots. So let's move on to the next one. So if we look, now for all these, I do require you guys to write the statement, which in class I'll repeat this. The reason why I need you guys to write the statement because you are already at that point in high school where you should get acquainted in writing your conclusions, just like as much you do for English writing. If you don't do this, unfortunately, you will have a hard time when you start going into the upper level math classes. So just FYI, good advice is that you should try it out. So now let's do one that's a little harder. Let me do number 6, right? Because I know my students are very eager to learn this, so let's do number 6. So if we try number 6, okay? So once again, P is my constant, and my Q it's my coefficient of the leading term. So in this case, a 5. So positive negative P, positive negative 21. So 1 times the 21, and the 3 times the 7, and that's about it. And the positive negative Q, in this case a 5. And in this case could be positive negative 1 and positive negative 5. And once again, once we use the rational root theorem, this is going to be, well, all the P's must be divided by all the Q's. Now, here's a trick to it. Once you're done with one of them, you can just scratch it out. So let's say right now I use the 1 over 1, the 1 over 5, and I'm done with the 1. So you can scratch it out. And then you do the positive minus 3 over 1 plus positive negative 3 over 5. Scratch it out. 7 over 1, 7 over 5. Scratch it out. Positive negative 21 over 1. And the positive negative 21 over 5. And when you simplify this, you get a positive negative 1 and a positive negative fifth, positive negative 3, positive negative 3/5, positive negative 7, and that's, well, not less, and then you get 7/5. Oops, should be a 21. And a positive negative 21 over 5. So if you count this correctly, it's a 1, 2, 3, 4, 5, 6, 7, 8. There are 8 times 2. There's 16. So my conclusion will be there are 16 possibilities or possible solutions, whichever one you want to use. But only, and let's see if we can get it from graphing, right? So what I'm going to do now is, again, I'm going to open up this one, this one, and it just happens to start with f of x for all of them, but it can start with g of x, it can start with p of x, h of x. It just depends who's the teacher. Let's do 2x squared minus 21. So let's check our results. So in this case, we have another predicament where, well, do we have fractions for this one? Yeah, we do, right? So maybe the 7/5 works out. So let's check it out. It's 7 over 5. That's 1.4, unfortunately. Let's try the other 5. And that's 4.2, right? And let's just double check to see if it's happening correctly. So if we start doing, let's say, a is equal to x. I'll say there's something cool. Well, let's switch with a, just so y'all can see what's. So if you switch them with a, you can use the slider just to see and make your life a little bit easier. So x equals 1. Just go ahead and add the slider, right? So when you add the slider, this is where you get. So if you do f of a, okay, it's not working out for some reason, but let's try it. Well, no, we'll forget about that. So if a is equal to 1, okay, did it work already? Because sometimes it works and sometimes it doesn't work. Okay. No, it's not working. So I try to do it. But anyway, unfortunately, none of these work out. Even if you substitute them. So in this case, I will say none are actual solutions. Since they are irrational. Or since f of x, has irrational solutions. Okay, so let's move on to the next one. I try to remember how to do it the way I used to do it, but I can't remember this one. So pardon me for that. All right, so let's look at another one. Let's look at number 17. I'll wrap it up with that. So if we look at number 17, all right, so my p in this case is going to be my constant of 12, and my q, it's going to be 3. So if you get the factors of 12, we already know that's positive negative 1 and positive negative 12, positive negative 2, positive negative 6, and positive negative 3, and positive negative 4. And then we have the positive negative q, and that's going to be positive negative 3. So the factor of positive negative 3, it's positive negative 1 and positive negative 3. So then we're going to go ahead and use this formula. Positive negative 1 over 1, positive negative 1 over 3, positive negative 1. Oops, we're already done with the 1. So let's move on with the 2. Positive negative 2 over 1, positive negative 2 over 3. So we're done with the 2. Positive negative 3 over 1, positive negative 3 over 3. Positive negative 4 over 1, positive negative 4 over 3, positive negative 6 over 1, positive negative 6 over 3, positive negative 12 over 1, and positive negative 12 over 3. Okay, now before I simplify this one, I need to urge you guys to please understand one situation we have here. So before I simplify, let me highlight a few pieces. So if you look at the first one, right? 1 divided by 1, that is a 1. And if you look within this list, you notice that there's another one that gives you a 1. And if you were looking at the 3 over 3, that's correct. Right? So these two are equivalent, and if it gives you the same number, you won't have to use it again. So then you go to the next one. So now the other one I want you to look at is the 2 over 1. And if you look around, there's another result or another operation that gives you the 2. In this case, 6 over 3. That's what we're going to use. And then there's one more I need you guys to look at. If you look at the 4 over 1, you notice the 12 over 3, it gives you also 4. So a rule about when you use the rational root theorem, you're not allowed to repeat the values that already come out. So in this case, I don't have to use the 3 over 3. I don't have to use the 6 over 3, and I don't have to use the 12 over 3. So positive negative p divided by q, that's going to give me positive negative 1, positive negative 1 over 3, positive negative 2, positive negative 2/3, positive negative 3, positive negative 4, positive negative 4/3, positive negative 6, positive negative 2. So in conclusion, for this part, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 18 solutions, but only, and this one does have actually solutions to work out. So again, just go ahead and graph it. Go ahead and graph it and see if you get them. So I'm gonna go ahead and graph this one. So f of x, 3x to the third power plus 9x squared plus 4x plus 12. And remarkably, it only has 1, which is the negative 3. So, but only the negative 3 is an actual solution. Or you can also say, since it's only 1, put f of x. You have to call it f of x because that's the function you're talking about. And if it would have been g of x, you can call g of x. But what was it? Negative 3 is its sole solution. Okay, and let me just copy paste this. Okay, now I need to warn you. For this particular section, guys, you are not allowed just to graph it and give me the one solution it has or the few solutions it has. I have to see the entire process. I have to see table charts. If I don't see the table charts or a way of refactoring, I will deduct points from your handout. So just make sure you use the method I'm trying to show you here. Once you use it, as I said, if you don't use it, I will deduct points from your grade. So if we have a quiz or a test for this tomorrow, you must also use these methods. You must write down your information. You'll write down your information. Again, I will start penalizing you. I'll only give you partial credit where credit is due. In those cases, some students don't like it, but I need to be fair with the other students. And again, just make sure you complete your work. Don't copy from somebody else. That's been another concern that's been brought to my attention. The students have been copying from other students because they have a group chat or something on WhatsApp or Facebook or Instagram. So you need to show your work. You can show your work. I cannot give you credit. I'm sorry. I don't know why I call it GFX or something else. Okay. So I'll leave it there for now, guys, and hopefully you guys have a great time with this section. And tomorrow I'll give you a little mini lecture too on it. Bye bye.